All right, so one more time to kind of catch everybody up. The reason we're finding the limiting reactant in this problem is what reason? Both reactants or more than one reactant have a given value, and they want you to determine something else about this particular reaction. So again, to find the limiting reactant, I'm giving you this cheat method, and the cheat method is the limiting reactant is equal to the number of moles divided by its coefficient. All right, so what was the number of moles you got for sodium? .544 moles, and then when you divided it by 2, what'd you get? 0.3 something? Okay, 0.27 what? 0.272. All right, and then water, 11 divided by 18.02. I need 3 sig figs. Okay. Now divide that by 2, which is obviously going to be less than the top one. You're killing me.
I thought you were already there.
What is 11 divided by 18? Thank you. You are killing me. No. All right, 0.6 what? 610. Then divide that by 2. So now it's point what? 305. So based on that, which one is now our limiting reactant? Thank you. Sodium is the one we're going to pick. So we're going to come up here and we're going to call this our LR. Okay. Now what do? Can you convert that to the grams of hydrogen? Yes. Let me ask you something though. Do you need to use the 12.5 grams, or is there something else you can use? Don't you already have the moles of sodium? Isn't it easier just to take that moles and go mole to mole from there? Okay. So again, you can and then go mole to mole and then mole to gram. So remember, you don't always have to go back to the original amount because you have at least solved for the moles of that substance. All right, so again, we're good there. All right, looking at this particular picture, and again, this is a particular model that I really want you guys to understand. Simply looking at this picture, okay, first and foremost, we know that hydrogen and water are going to form, hydrogen and oxygen are going to form H2O, correct? If I did not give you this down here at the bottom, if I were to take this part off, but you could still see the colors, what color does the oxygen represent? How do you know it's red? Okay. When you look at the water molecule, it's 1 oxygen for every 2 hydrogens, right? That's what I want you to get. That's what I want you to understand. What is the limiting reactant in this particular reaction, and how do you know? Simply based off the picture. How do you know it's hydrogen? What do you have remaining? You've got 2 oxygen molecules left over. However, if I did give you the initial numbers, 10 hydrogens and 7 oxygens, what would you have assumed to probably be the limiting reactant? Why? You would assume it's oxygen because it has the least amount, right? However, what you just said makes sense. It's a 2 hydrogen to 1 oxygen ratio. So, how many hydrogen molecules specifically would I need to use up all of the oxygens? 14. But I only have how many? 10. Exactly. So if I put in 4 more hydrogen molecules. Could I use up those excess?
Yeah.
Yes. This is the kind of stuff that you're going to be seeing on that AP exam. You're going to be seeing these kind of pictures. You need to understand how they work and how they relate. Okay? It's very important that you grasp that. All right, the limiting reactant is the reactant present in the smallest stoichiometric amount. So again, it'll run out first. Okay? All right, we've already talked about that. I want you to do this one. Is that already filled in for you guys, or is it blank? Wonderful. All that is a gram to gram conversion, right? Okay. Do you really need to do that? That's a 3-step gram to gram. Pretty simple. Okay. Actual versus theoretical. Remember, theoretical is what you do on paper. Please write this word in beside this. It's based on Stoich. Again, it's based on the stoichiometry. Okay, it's what mathematically and on paper you should achieve. And then actual is what do you do? It's actually what you do in the lab. Okay? And then I've stated this a lot of times, rarely do you get 100%. Really in laboratory experiments, we have the 70% rule. If you're within 70%, you're doing pretty well, okay, depending upon the lab itself. But 70% is normally what we're trying to get. Okay? All right. We're going to skip this. This is basic. 5.2 grams of copper nitrate is obtained. How many grams of NO2 should also have formed? Basically, you're just going from grams of copper 2 nitrate to grams of nitrogen oxide. Real simple. That's a 3-step gram to gram. What would be your mole to mole conversion there, or mole to mole ratio? 3 to 2. Okay. So again, you know how to do that. I'm not going to waste your time on that one. All right, so hopefully that's what you wrote down on this one right here. Now, there's 2 things I want to talk about. Number 1, the question is what mass of gaseous carbon dioxide can be absorbed? So really what we're asking here is how many grams of that. By the way, I didn't balance that. Just 2? Okay, that'll work. All right, so the question here is if I start with 1 kilogram, 1 kilogram of lithium hydroxide, how many grams of carbon dioxide can be formed? Well, here's the issue here. That's not really a great way to start this problem out. Why? Because when you solve for the molar mass of lithium hydroxide, what will that unit be in? Grams. So what I would recommend doing is changing this to what? 1,000 grams. That is a much easier way to start things. Just like whenever we see, again, we'll get into this later, when they write things in milliliters, it's going to make your math so much simpler if you'll go ahead and change it to liters, or vice versa. If we need it in milliliters, go ahead and get it. So in this case, I would definitely change it. And the last thing Parker said that I taught last year, and some of you may remember this, sometimes it makes life a little bit easier. If you ever see hydroxide on one side and you see water on the other, in terms of balancing and in terms of making things look similar, if you want to write water as HOH, it means the exact same thing. It's equivalent. Yes, sir. No. I mean, yeah, I guess hydrogen hydroxide, that's a good question. I've never actually thought about it that way. You just need to realize that it's water that you're working with. It just, especially with acid-base reactions, it makes balancing them so much simpler. And you'll notice whenever we get into electrochem, it's going to be a lot easier to work with a HOH than it is to work with water. Okay, much simpler. So again, and then you can go from gram to gram, and it'd be a 3-step equation. But I wanted you to practice writing that balanced equation. All right, percent yield. This is something I make sure you understand is basically it's the actual over theoretical. It's what you should get. Let's try that again. Comparing how much you should get versus what you do get. So it's actually what you got, and again, this is how I normally say it. It's what you got divided by what you want. Okay? It's what you got. Sorry, that was not supposed to go through that. So what you got divided by what you want. Okay? The actual over theoretical. Got over want. Okay? All right. Find the percent yield for that one right there. All right, what percentage did you guys get? Thanks. 82. Okay. Now, this is something that's going to change a little bit from last year the way I taught it. Last year I always said I want just a whole number percentage. This year, let's go with this number of significant figures in the problem. So what would it be percentage-wise with 81.8? Okay. So 81.8%. Did you do a pretty good job? I'd say so. If I told you right now that you were going to get an 81% on your first test, a lot of you may take it. Some of you won't. I would hope you wouldn't. I would hope you want better than that. Okay. All right. Baking soda has often been used as an antacid, and it neutralizes excess hydrochloric acid, right? So basically, this is something you would put in your stomach if you have, help me out there for a second. Heartburn. Thank you. That's what I'm looking for. All right. Created by the stomach. So, first of all, how would you actually name that right there instead of saying baking soda? Sodium hydrogen carbonate. That's all it is. Sometimes you'll hear it as sodium bicarbonate, but this is sodium hydrogen carbonate. Okay? What's wrong? Yeah, very good question. Very good question. Do I need to explain that? Okay. All right, let's look at this. All right, first of all, hydrogen carbonate, HCO3 2 negative. So when you have this, when you combine them, what's going to happen to one of those charges? It's going to kind of neutralize one of them. So that is hydrogen carbonate's charge. Well, then when you put Na in front of it, what happens? That's what happens. So when you put the polyatomic together, the hydrogen neutralizes one of the charges, but it still maintains its polyatomic charge. Okay, so that's why it looks like that. All right, HCl, blah, 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 blah. Milk of magnesia is an aqueous suspension of magnesium hydroxide, also used as an antacid. Milk of magnesia? Yes. I mean, I have a bottle of it. I can show it to you. It's also used as an antacid. So here's my question. Should you use baking soda or Tums, or should you use milk of magnesia in order to be an effective antacid. So this is what I want. This is what I want to happen. Jordan and Cannon, this side. I want you guys to take 1 gram of baking soda. Okay, and what I want you to do is I want you to convert it to grams of hydrochloric acid. Okay, and then Parker, Seth, and y'all on this side, I want you to take 1 gram of milk of magnesia, and I want you to convert it to grams of hydrochloric acid. And we're going to determine which one will neutralize more grams of HCl per 1 gram of hydrochloric acid. This is what? This is a real life scenario. Exactly right. So basically, when you get done with this, you're going to be able to determine which one is a better antacid. Okay. All right. So based off of the 3-step stoichiometric conversion, it should have been pretty simple to this. Now, I know that I can plug in several values already here. I know I can have a 1 here and a 1 here for my mole to gram conversions. Those are pretty simple. I can go ahead and do my mole to mole. What is my top to bottom mole to mole ratio for my sodium hydrogen carbonate or my baking soda? It's a 1 to 1 here. All right, what about for my magnesium hydroxide? It's a 2 to 1. That's interesting. That's interesting. Okay. Do what? Okay. All right. What is my molar mass of sodium hydrogen carbonate? 84.01. All right, what about for hydrochloric acid? 36.46. Okay. All right, so 36.46. All right, what about for magnesium hydroxide? Sounds right. Okay. So, how many grams of hydrochloric acid could you have dissolved with 1 gram of sodium hydrogen carbonate? 44? 0.434. 0.434 grams of HCl. Okay. All right. Other side. How many grams of magnesium hydroxide could you get? Wow. 1.25 grams of HCl. So you actually dissolve more hydrochloric acid with magnesium hydroxide than you do with sodium hydrogen carbonate. You actually dissolve more than you actually started with. So which one is obviously the better choice for an antacid? Magnesium hydroxide. Now, don't throw anything at me, but you actually could have stopped a step short here. Why? Did you really have to find the number of grams? No, what could you have really found? You really could have stopped after this point right here, and you could have found your answer. You could have compared them in moles. I wanted you to go to one more step just so you could see it in terms of grams, because I think you understand grams better than you understand moles. Now, there's one last thing. Let's actually talk about the chemistry behind why this is true. If you mix sodium hydrogen carbonate, you're going to mix it with an acid. And then you're taking magnesium hydroxide and you're mixing it with an acid. Shouldn't scientifically and chemically it make more sense to do magnesium hydroxide? Why? It's a base. So you technically have, for every 2 hydroxide ions, what are you going to neutralize? 1 hydrogen ion. And what are you going to turn it into? Water. However, when you put in sodium hydrogen carbonate, what is going to be there to neutralize that hydrogen? Nothing. Okay. What's really going to happen is that this carbonate ion is going to turn into CO2. It's going to turn into a gas, which will make you burp. Okay. So why do you think whenever you pour baking soda on stuff, sometimes it bubbles? That's why, because you're producing that carbon dioxide gas. So that's exactly what's happening here. So chemically speaking, it should make more sense that we use a strong base to neutralize a strong acid. But this proves the math of why magnesium hydroxide is a much better neutralizer than the baking soda. Okay? What's wrong? It's an antacid. Yeah, it's basically that's what it is. I mean, you can go to the store and buy milk of magnesia. I don't think it's very expensive at all. I mean, I'll show it to you in just a second, but yeah. All right, molarity. This class, did y'all get to molarity last year? Do you remember, Jordan? Justin? Okay. All right. This is probably the most important topic in all of AP chemistry. This is more important than stoichiometry, is your understanding of molarity. What is molarity? It's how concentrated something is. Here's the best way I can explain this. If you go to McDonald's and you order some sweet tea, how would you explain its concentration? How sweet it is. How do you physically determine how sweet it is? How much sugar is dissolved in what? Into the water, okay? Or the tea, if you will. So it's how much sugar is put and stirred in. So the more sugar that's put in, we call it more sweet or more or whatever, okay? The less sugar you put in, the more dilute it is, okay? So here's the deal. The way molarity works is we're going to take the number of moles of that substance and we're going to divide it by how much volume of a substance you're putting it in. So it's going to be the moles of the solute. How much sugar you're putting it in. If you walked into McDonald's and asked the person at McDonald's, so how many moles of sugar did you put in there? They're probably going to look at you real funny because they probably have no clue what you're talking about. But can you get moles from how much they're putting it in? Yeah, what would you need to know? The grams. How big is that bag of sugar they're pouring in there? Probably 5 pounds worth. But it's how many moles of sugar you're putting it in for every gallon, or it's not really gallon, I should say liter because it's liters, of tea. That's the simplest way to look at it. So every time I pour in more sugar, what's going to happen to the concentration of the tea? It's going to get sweeter and more concentrated and more concentrated. What if I leave the sugar alone and pour in more and more and more water? More dilute. So what's going to change? Your concentration. Okay? Your molarity will change. So when moles goes up, it becomes more concentrated. When volume goes up, it becomes less concentrated. This is going to make or break you in this class, is understanding how concentration works. One thing I need you to understand is that whenever you see molarity, use brackets. So if I'm talking about the concentration of, that's not supposed to look like that. If I'm talking concentration of NaCl, if you see brackets around something, that's going to stand for molarity. It's going to stand for concentration. It's important that you recognize that. Okay. So what is the molarity of a solution that contains 34.2 grams of NaCl in 575 milliliters of solution? First and foremost, is something wrong with the units that they've given us? And I'm going to forewarn you, those jerks at College Board that make this test do this almost every single question. But here's the deal that I need you to understand. You've got to get past the little stuff. You've got to get over the fact that, you know what, this is going to happen. I'm going to have to deal with it. Don't let it stress you out. Expect them to do this. But the good news is guess what? Simply by converting grams to moles, guess what? You get a point. You should beg for them to do this. The simpler the steps they give you in order to get to the bigger picture, you're earning points every single step of the way. So if they ask you to find a gram-to-gram relationship, be excited about that. Be pumped up because guess what? I've got a point. I can do this. Anytime they ask you to do the basics, be excited about it because it's a guaranteed point every single time that you do it. They're not going to ask you to do something and not give you credit for doing it. All right, so 34.2 grams of NaCl. Let's try that again. That's a C. That's an L. I always forget the mass of sodium chloride. That's it, 58.44. Thank you. I don't know why I always forget it, but I do. All right, so in 1 mole, and I'm trying, I promise. I need a new pen so bad. 58.44 grams. Okay. Do what? No, it's this pen. I can't buy these. The media center has to buy them. All right, so somebody do 34.2 divided by 58.44, and then give me that answer, please. 0.585 moles of NaCl. Now, remember, molarity is moles divided by what, Clay? Liters, but what's wrong? Okay, so that's a simple conversion. You don't even you shouldn't have to do anything in your head. All you have to do is move what? Decimal which way? So it's going to be 0.575 liters. And so here's how you can write it. Go ahead and give me that answer, please. I need, well, duh. I need 2 more digits at least. 1.01, 02. You can write it like that. Or how else could you write it? They're very good. I didn't even think about that. Or you could write it 1.02 moles over liters. Or, well, you said it? Brackets. If you write the brackets, do you have to include the M? No. Brackets are sufficient. You could write it all 3 of those, and all 3 of those stand for the exact same thing. They all stand for concentration. Okay. I think there's 3 more. You guys do the last 3, and I'm going to work and we'll call it quits for the day.